Okay, this is nice. This is a different venue than last year. Roast Summit last year was hosted in this enormous room where everyone was sitting on sofas. And this year we're in another enormous room, but you're on less comfortable chairs, but it looks better, so there's that. I am from Eugene, Oregon. Go Ducks, we're having a good year. So things are going well, and as you can see, I'm a company man. I'm wearing the green. I drove up here this morning, and I've been a little busy. I want to give you 2 update slides before we get into water for coffee. So update slide number 1, I had a kid. Thank you. And so his name's William. You can see I'm a Texans fan, and for my birthday, which was also yesterday, he got given Texans onesies. So now he can watch the game with me this weekend, and we're gonna have a great time. He's doing really well. He's 7 months old now, and that's occupied a lot of time. I fortunately don't have a real job. As you saw on the first slide, I'm a professor of chemistry, which means I only have to teach and run my research group. So at nighttime, I spent the last 6 months while I was on leave writing Water for Coffee, the book that I promised you was coming. It has been sent to China. It is being printed, so it is coming. It's gonna be here before Christmas, so keep an eye out. The other thing I wanted to tell you about was last time, how many people here were at Roast Summit last year? So a couple of you, and some of you might recall what I talked about. I basically spoke about putting electrodes, pieces of metal inside liquids, in this case obviously coffee, and measuring what was dissolved inside the coffee in real time so that you could in principle make statements about how you change brew parameters and how it affects what you're tasting. Well, we realized that if we just sat at certain voltages, we could start to affect the populations of those molecules. So we could take things that were imparting bitterness and annihilate them. So hiding behind low quality coffee, there's a lot of high quality flavors, but your tongue was just tasting supreme bitterness. So what we did was actually, we incorporated a company at the beginning of this year, and I wanted to just show you one of the things we can do. So over here, this is Starbucks Pike Place. And basically, you just apply electricity, and starting with something that is supremely bitter, as you all are very familiar with, I'm sure, over time, of a span of 2 seconds, you half the bitterness, you start to bring in sweetness and acidity, and after about, let's say, 1 minute of treatment, which is just passing electricity between these 2 sheets of metal, the Starbucks Pike Place turns into pecan pie. It turns into something that is actually good. And so I'm not really an enterprising person. Many of you know this if you've seen me speak before. I'm an educator, but I'm pretty excited about it. We're doing the whole startup thing, and I've never thought I'd be in that world, but I'm in it now. So this has made me want to mention this because all of you are in business in some capacity, and I have a new level of respect. And in addition to the level of respect I already had for working in coffee and doing all the things with people, I now have a new level of respect for you working in business. So I'm learning a lot from being here. So I wanted to just thank you for welcoming me, not nominally in your community, in again. So thank you for that. All right. We're doing Water for Coffee. Anyone ever read the 2015 version of this book? Couple. Yeah, it was brutal. So I deleted every single page and started again. In part because I wrote it when I was 10 years younger than I am today. And I was 10 years worse at writing, and now I've written a lot more, and this book is now a lot better. It's a lot more difficult. So what I'm gonna do is now tell you about everything that's in that book that matters to you, and then hopefully you'll learn something by the end of it. In specialty coffee, we have a problem because we write flavor notes on bags, we talk about flavors, and implicitly this is a contract. So if I were to tell you, you come into my cafe, that you're going to purchase a cup of coffee for $5 and it should exhibit lemon, bergamot, and watermelon flavors, and you don't taste that as a consumer. Instead, you taste something like salmiakki, dirt, and Brussels sprouts. I would say that that would be a failure. I'm not sure who failed, right? So that's the question. And I tried to break it down in this pie chart for you, and the way I like to think about this is that if you start with really low quality green coffee, the ceiling of the quality of that cup is going to be limited. And so I'm going to put 50% of the quality of that cup's ceiling comes from how high quality the green is. But the roasters are making decisions when they're turning green to brown. And so at some point, they're going to stop roasting in some way. They're going to cup that coffee, and implicitly, they're brewing it with water they have access to. And so they're making a decision that the way they roasted it tastes good with the water they have. And so I attribute water and roast equal parts, 50-50. And then the final step, which is the part that is probably the most annoying to all of us in this community, is that the easiest thing to blame is the barista or the grinder or the way that you actually prepared it. Obviously, that's frustrating because in principle, we could do this reproducibly, and that's what chemistry is I write a paper and I say how I did something, and another person somewhere else in the world should therefore be able to reproduce it. So I believe that equipment doesn't actually matter that much once you pass like a certain minimum level of quality of grind, or you get the idea. But I want to focus very specifically on water chemistry and its implicit relationship with the quality of green coffee and the roast. In order to do that, we could just skip to like the last graph, literally the last slide, and we could just talk through it for 2 hours. Or I'm going to start with the way I like to do it, which is start with atoms and build up so you understand why this is complicated. So with that in mind, we have to go to the level of knowledge that the universe had 13.8 billion years ago, which is we literally knew nothing. Let's assume that we all know nothing about chemistry, okay? And we're going to start with atoms. So the most simple atom in the universe is the hydrogen atom. It has one positive charge in the middle and it has a negative charge on the outside. The positive is a proton, and the periphery, it's an electron. Now they tend to like to be near one another. Classically, we would say this is because pluses and minuses are attracted, but then obviously there's some other quantum mechanical stuff that we are not going to talk about. If you put two atoms together, they might want to be near each other. And so we would call that forming a bond. And of course, we're going to define the zero energy difference as having the atoms very far apart as if they don't see one another. But as you bring them nearby, that bond might stabilize them. There's going to be some equilibrium bond length right here. If you push them too close together, that becomes disfavorable because remember the positive charges in the middle are both positive, and so they will repel one another. So to hold the atoms close together actually costs you energy. And so that's why it has this shape right here. So it's high energy over here, equilibrium there, and non-interacting on that end. Now, that's just one atom on the periodic table, but if you want to build other atoms heavier than that of hydrogen, you need to add more protons, more positive charges into the nucleus. And so the way that stars do this is they take two hydrogen atoms, and they put them together, and then they add a couple of neutral particles called neutrons to the nucleus. And when you do that, two hydrogens plus a couple of neutrons makes helium, which is the next element on the periodic table. And if you want to make lithium, you're going to need to add helium to hydrogen plus two more neutrons, and then you get lithium. And if you want to make boron, then you got to add lithium plus the helium you've just made, and then you get the idea. Each one of these is subsequently releasing energy, but the density of the atoms in the star is increasing over time because you can see these could be far apart. Now they're really close together, so density is going up. So as a result, the density of the star over time is increasing, and as a result, the star is going to collapse. And when that happens, that gives you enough energy to form all the other elements on the periodic table. And people have been studying this for a long time. So going back to Mendeleev, you could think of him as the father of the periodic table. This is his seminal paper that he published 1869. And this looks a bit like a periodic table, except for tilted on its side. But what I like about this is this captures the essence of chemistry. The discipline is not remembering the periodic table. It's about using it to make predictions. And he was doing it already. He knew that something weighed 45, but he didn't know what to call it. And he also knew something was called thallium, but he didn't know what its exact mass was. You get the idea. These were predictions. These were way ahead of their time. Now we go through and fill it all out. And so this is what the periodic table looks like today. There's a lot of information on a periodic table. We don't need to know all of the elements on the periodic table. In fact, very often, someone might come up to me, usually someone's child, and ask me what element number 32 is. I have no idea. That's why we have a periodic table. So it's written down for exactly this reason. So I'm not expecting you all to remember this stuff. The point of it is these are tools that we use. This is our brew control chart, okay? So the idea here, though, is that it's ordered in some way. So the first thing is the number there is the number of protons in the nucleus. We already went through hydrogen forming helium, forming lithium, and so on. The next thing is the atomic symbol. Typically, these are the first letter that maps to the name of the element in English, but there are some examples where the names are not in English, so the letters do not map to them. For example, if you ever wondered why tungsten is W, you can look it up in your own time. So the atomic name is typically in English, is written in English, so hydrogen, helium, etc. I'm just wondering if there's an example. There's no example that I've shown here where it's diverging, but you get the point. Potassium. Anyone know what it's actually called? It's K-A-S-I-U-M, casium. There you go. We all learned something. Very good. So, so there's a few other things on the periodic table. Electronegativity, which we're going to talk about in a second, and stable oxidation states. So what this is how many extra or fewer electrons that atom tends to like. And so if you see a positive, it's lost an electron. That is, hydrogen is very happy to lose one electron to become H+. In other words, just a proton. Go to the other side of the periodic table, fluorine is very happy to receive that electron and become fluoride, which is F-. And so you can start to use this to build molecules based on just those charges alone. What dictates those charges is actually that electronegativity number. So typically, you're going to think of this as lithium is electronegativity of something close to 0. It's very happy to lose its electron. Fluorine, something close to 4, so this range is 0 to 4, very happy to receive it. And so you can start thinking, oh, well, if I put lithium with fluorine, lithium's going to go 1+ and fluorine's going to go 1-. All right, so here's an example. Hydrogen and oxygen. When you put these two together, you get H2O. And there's 2 of them because you got to get 2 pluses to balance out that 2-. Pretty easy. How about this one? Calcium, carbon, and oxygen. Some of you are probably looking at this going, well, we could achieve a neutral compound by just having calcium and oxygen, 2+ for calcium and 2- for oxygen. Sure, that's cheating because I need carbon in there as well, okay? So calcium oxide is stable, but what I'm actually asking you to do is think a little bit more. So calcium 2+, carbon 4+, oxygen 2- makes calcium carbonate or lime scale. This is how we start thinking about building things. It's basically Lego for adults. Okay, you just learned about 13.8 billion years of chemistry. We're now up to 140, the knowledge of Mendeleev, right? We have a periodic table. We understand the building blocks we can play with. Let's start using them to make something. And so that's where molecules come in. So no longer are we thinking about individual atoms, but rather now combinations of those atoms. And the neat thing about the combinations is that they are always greater than the sum of their parts. So if I take H and O to make water, the properties of H2O vastly different than that of H and O. So you can appreciate the level of complexity is starting to compound. In part, that's because when you start with only one atom, you only have to deal with the identity of that atom. Is it hydrogen? Is it lithium? As you start to move to 2 atoms, if they are different atoms, then you might have a difference in that electronegativity, so the interaction might be polar. One side will pull harder than the other side on those electrons. If they're the same, it's nonpolar. With 3 atoms, there's now a bond angle you have to worry about because those 3 may be in a perfect line or they may not be. And with 4 atoms, we have to then worry about something called the dihedral or torsional angle, an abstract concept, but if you imagine my fists as 2 atoms and my elbows as 2, it's the bond angle that you see when you look down my elbows. So that would be 90 degrees. So this fist to this fist is 90 degrees separated, right? So that's a dihedral. And with that, if you knew all of the types of atoms, their bond lengths, and the angles and the dihedrals, you could describe any molecule that could form in the universe. Here are some. This one here, 2,4,6-trichloroanisole, is one of the molecules that's associated with the wet dog smell in cork-tainted wine. I like that molecule. Eugenol, this one is a woody flavor that shows up in bourbon. It's valued in barrel-aged products. It is not valued in coffee. That's interesting. One molecule in one format, not valued in another format. Citric acid, obviously self-explanatory. Let's go for another fun one, amoxicillin down here on the bottom right. So this is obviously an antibiotic that we've all hopefully not had to have, but we probably have all been exposed to it at some point. You get the idea it's growing in complexity. And I'm standing up here giving you a lecture about these things, and I'm actually going to talk to you about this one. So it must be simple, right? It's so much smaller than everything else. All right, so water is not one molecule. Water is a collection of molecules that happen to exist as a liquid at room temperature and pressure on Earth. And as a result, if you look at the geometry of water, you can see that it's bent. So it's not 180 degrees between these 2 hydrogens. It's more like 104.5 degrees. And that gives rise to oxygen having a negative charge and hydrogens now having a positive, and that means water's polar. So what it does is it tends to orient so that the hydrogens of one water point to the oxygen of another one and forms these little networks. In doing so, it can help solvate things like calcium. It can surround chloride and bicarbonate, and it even forms cages around insoluble things like octane. Let's take a closer look. Oh, actually, I forgot about this slide. Let's do this real quick. So in addition to it being a bulk material that dissolves things, it also has this unusual feature, which is that at a certain temperature and pressure regime, water can exist as a liquid, a gas, and a solid on Earth. That's weird. Dry ice, which is solid carbon dioxide, that exists as a solid, and then also immediately turns into a gas. We don't access liquid carbon dioxide on Earth. So that makes water unusual that we can see all three phases at a pretty reasonable temperature and pretty reasonable pressure. Okay, it's low pressure and low temperature, but it's something we can access. All right, looking more closely. We already appreciate this interaction at the smallest scale, which is the hydrogen bond, hydrogen binding to oxygen. We know that it can form, at the minimum, these tiny little hexagons, because that's the simplest way you could put three water molecules together. We can stabilize things like chloride by having protons point towards protons here pointing towards chlorine there. And conversely, we can stabilize positively charged things like calcium by having oxygen point towards it. The snowflake has 6 sides, because at the molecular level, when water cools down to freezing, you trap in this hexagonal structure, which grows out to make this hexagonal structure you see here. So you may think that I'm talking about length scales and complexities that you don't interact with every day, but you do. You see it all the time. It's just that it's coming from something that's it's on the molecular level. I want to highlight one other thing, is that water is really good at solvating things that are not polar. For example, petrol. The reason, though, it tends to separate is that the solubility is limited not by the fact water can form cages, but because those cages need a lot of order to keep them surrounding that molecule. So water's happy to do it to a point, but at some point it's better for the octane to separate and float on top of the water. And so you experience this all the time. We pour hot water on coffee, we start extracting things, they end up in the water, but then you start smelling things. And those things that you're smelling are things that the water is now releasing because for whatever reason, it's better for those molecules to exit the cup than it is to stay in the cup. So this is the basis of why you get phase separation. In octane's case, that one just floats as a liquid because the pressure and temperature of boiling of octane make it a liquid in most conditions that we experience. The other thing is water can dissolve carbon dioxide. That's really important. So while CO2 is not polar because oxygen on both sides pulls equally in both directions, oxygen itself is negatively charged, and so the protons from water can point towards it. And this is important because if the concentration of CO2 were to increase in the atmosphere, then the solvation of CO2 in water would increase as well. We're going to see a reaction later on where CO2 dissolving in water makes the water acidic, but this is obviously a macroscopic problem because with increasing CO2 and increasing temperature on Earth, it makes the oceans become acidic, which then kills the coral and the fish and the people, okay? So you get the idea, we care about that. Okay, so you're like, Chris, what the hell are we talking about? Here. Take home message. If the molecules have oxygen and nitrogen on their periphery, they're gonna dissolve in water. And if they get really big, they're gonna probably not like to dissolve in water as much because you're gonna need more water molecules pointing towards it to dissolve it. And then finally, generally, polar molecules like to stay in the water. Okay. This brings us to a very profound finding in 1903, the third Nobel Prize in Chemistry awarded to Arrhenius for the discovery that if I take table salt, sodium chloride, and I put it in water, it splits into sodium plus and chloride minus, rather than sodium 0 and chlorine 0. This sounds obvious now, but back when you knew nothing, this was a big deal. That's a Nobel Prize there for the dissolution or electrolytic dissolution of ions. What I'm really saying here is that if I take calcium chloride and dissolve it in water, it turns into calcium 2 plus and chloride minus. And well, it should have a 2 in front of it because there's 2 of them, but you get the point. The neat thing about this type of principle is that you can take things that are nominally not stable. Magnesium bis bicarbonate is not something one can hold. This is not a compound that exists as a solid. But in water, you can have magnesium and 2 bicarbonates floating around. That's totally fine. So water actually also additionally allows you to stabilize things that aren't stable as solids themselves. Water is complicated. So there's a highlight. Okay. So with that in mind, we now have to do a little bit of counting. So we have to basically learn Gen Chem here in one slide. Okay. Imagine you're in a hotel and you see an elevator whizzing down the floors and hit the ground and it explodes. And you then look at the weight rating for the elevator and you see that the elevator could have held 9 people or 1 horse or whatever, right? And you don't know, though, what was in that elevator. You just simply know that the elevator has failed. And now I'm going to ask you, was it because we put in 10 people in that elevator? Was it because there was 2 horses in the elevator? You don't know, right? And so the problem with this is that if all you did was weigh the elevator, you would have no idea of what caused it to fail. Was it one of these things, or was it simply that we exceeded the weight limit? Chemists have dealt with this problem by learning to count the number of things and then assigning the weight to the specific item that we're counting. We have a special number for this, but before we talk about the number, I want to talk about other special numbers in the universe. You're going to help me here. There's a special name for the number 12 when you buy 12 of something. What is it? A dozen. There's a special number for the number that comes after 99. It's got a name. 100. So when we're saying these words, we know what they mean. So now I'm going to teach you another word for another special number. And all it is this number here. It's a mole. Okay, great. So now you know that when I say a mole, it's just counting something. It's the same as a dozen or 100 or whatever. It's not a secret chemistry thing. It's just we have to assign a word to a really big number. But the number has a physical meaning as well. So remember that carbon here, its atomic mass here is 12. If I hold 12 grams of carbon, I'm holding this number of carbon atoms. I'm holding 1 mole of carbon. Let's do it for magnesium. If I'm holding 24 grams of magnesium, I'm holding 1 mole of magnesium. Let's flip the question around. If I'm holding 1 mole of calcium, how much does it weigh? 40 grams. Yes. All right. You are doing great. You're like way better than Gen Chem. Okay. So why this matters is that 1 mole is just a number. So if I have 1 mole of magnesium and I have 1 mole of calcium, those are the same number of magnesium and calcium, but because calcium weighs 60% more than magnesium, you actually have, if you're doing it by mass, you have way fewer calcium atoms than you do magnesium atoms. Let's give a worked example. If I have a water that is 100 milligrams per liter of magnesium, because it weighs less than calcium, it has 4.1 thousandths of a mole contained within. Millimole, whatever, like a millimeter, a millimole. If I have 100 milligrams per liter of calcium, that water only contains 2.5 millimole of calcium, which means if we talk about water concentrations in milligrams per liter or ppm, we have no idea what the heck we're talking about because we have no idea whether we're talking about magnesium or calcium, and you can see there's a really big difference in terms of mass. So this is the problem. So chemists don't count in grams or milligrams per liter. We count in mole per liter and say mole per liter of magnesium, mole per liter of bicarbonate. Nice. Let's count a reaction. We dissolve something like acetic acid in water. This is the reaction that's going to occur. It's acetic acid plus water turns into acetate plus hydronium. Now imagine that we start at pH neutral water, so a pH of 7. So we're going to start somewhere around here, okay? When we start to dissolve acetic acid in water, the first thing that's going to happen is some of them are going to hand off their proton to water to make hydronium and acetate, as drawn down here and as shown here. And then this water might shuffle onwards to do this. And at this point, the acetate and the hydronium are separated from one another. They're floating around in solution. Okay. How much of this turns into this pair? It's a good question. Well, it turns out that when you measure the pH of a liquid, what you're measuring is how much of this there is. But if you want to talk about how much acid is in the water, you need to measure how much of that there is. And you can imagine then that those are actually quite different things. And it does depend on the extent to which this reaction has occurred. So you can see the pH starts to drop with the more acid that you put in, but inevitably the critical point here is that pH depends on this stuff, What we taste when we taste acid is the remaining that did not partake in that reaction. We're tasting that. So we taste vinegar as vinegar because we're perceiving this molecule, not this molecule. Okay. So all that pH actually is just a way of counting how much hydronium is in solution. That is, the concentration of hydronium plotted on a logarithmic scale. And so with this reaction, we can say the extent to which the reaction occurs can be monitored by the change in pH, because we just look at how much hydronium there is, and that's the product of the reaction. So that's nice. The pH scale is handy. Okay, we could do math. I love math, so we could do some math. Or I could just show you this picture, which just says that neutral water is 7 because it has this amount of hydronium in it. And as we add more acid to water, you start to shift the pH this way towards a point where pH 0 is 1 mole per liter hydronium. Somewhere in the middle there are the things that we eat. Coffee is always between 4.5 and 5.5, independent of how you brewed it, how you roasted it, origin, processing method, you name it. So coffee is remarkably consistent in that pH range of about 1 pH unit. All right, good. We're doing good. How much time do we have? Another hour? Okay, all right, good. All right. Well, we're 15 minutes ahead of schedule, so this is going well. So that's the knowledge. You've now got the knowledge to the point of the beginning of the talk, where you've walked in here, many of you appreciated that water chemistry matters for coffee flavor, and now you can appreciate that there's like a lot of background stuff that's happening, and maybe you've gleaned 10% of what I've said, which is 10% more than you had before I started talking. So that's a win. You are pH 7.25 to 7.45, independent of what you eat. Now, how is that possible? If I do a shot of vinegar right now, I'm unfortunately not sticking around for long, but I would love to do picklebacks with you after the talk. And if we were to do that, we would drink some bourbon and it would be fine. It wouldn't adjust my pH. And then we would drink some pickle juice, and that's basically vinegar. And if we did that and you didn't have a way of dealing with that increased acid in your body, you would die. But we don't die. We simply deal with the incoming acid somehow. It's because your body is filled with this molecule bicarbonate. Now, the way it gets in there in the very first place is you can imagine breathing in carbon dioxide. So carbon dioxide will react with water, as I mentioned, in the oceans. It then turns into carbonic acid. Carbonic acid is an acid, so it's going to lose one of its hydrogens the same way I just showed you for acetic acid. And when it does that, it turns into bicarbonate. Nice. That's not exactly how you came to be buffered like this, but you get the point, is that you have a bunch of this stuff in you. The neat thing about bicarbonate is that if you add acid, a source of H, to this molecule, it becomes carbonic acid. So when you do a shot of vinegar, all the bicarb in your body is going to start working so that the water doesn't feel the acid, but rather the bicarb deals with it. And then all you have to do so that you don't die is just breathe out so that you release the CO2. What if you add base to bicarbonate? So somehow you accidentally drank some drain cleaner, some potassium or sodium hydroxide. You might die, okay? But bicarbonate's going to do its very best before you die, okay? And the way it's going to do it is it's going to take the hydroxide from the drain cleaner, is going to steal this hydrogen. This molecule is going to turn into carbonate. And as a result, this carbonate now did not allow the water to feel the impact of the hydroxide you've added. It took all of the responsibility of that itself. So the pH of the water doesn't change. You form carbonate, and we have to eliminate this somehow. And the way that happens in your body, unfortunately, is that you eliminate it through your kidneys, typically as a kidney stone. It's unpleasant, but you're not dead, okay? So your body's good at this. What I want you to take from this is bicarbonate handles the addition of acid. So if you have a liquid that has bicarbonate and you add acid, the pH of the solution does not change really, and instead bicarbonate is going to destroy all of those acid molecules so that you don't perceive them as acidic. Let's have a look at the atomic level of what's happening. On the left-hand side, this water here has no bicarbonate. Now, I know that bicarbonate's a bit tricky because it looks a little bit like acetic acid. Let's just take a second to get this. See how this is like dead end here, not an oxygen? That's acetic acid. See how this one looks basically the same, but it has an oxygen? That's bicarbonate, okay? So this is bicarbonate, this is acetic acid. So there's no bicarbonate over here. So when I dissolve that acid in water, what we end up with is some of them form hydronium. Some of them are now the thing that's lost that proton, so it's floating around as a base. And most of them exist as that acid floating around in solution. So in this case, this water's pH is dropping. There's still acid floating around in solution, so we're going to taste those acidic molecules. Overall, the pH has changed. On this side, we now have bicarbonate. We have the same acid molecules that we're going to add. And what you'll note is I've drawn it so that no hydronium forms. So on this side, no H3O+, and instead, a conjugate base, which is that molecule, does form, and carbonic acid. We did not make more hydronium, therefore the pH does not change, but we've destroyed all of those acid molecules, therefore we can't taste them. Okay. Because all coffee has a pH of between 4.5 and 5.5, and bicarbonate loves to try and maintain a pH of 6.3, you can imagine we have a problem. Because if I use bicarbonate-rich water and coffee's trying to go acidic, and bicarbonate's job is to make sure that doesn't happen, bicarbonate's going to do everything possible to make sure you can't taste acid. So the summary of what bicarbonate does is it reduces pH swings, it's going to mute the acidity in the cup, and it's going to leave behind molecules, those conjugate bases, the acetate rather than the acetic acid. And acetate is actually bitter and basic and weird. It tastes like fishy. And so if you have bicarbonate around, you see instead of a cup tasting bright and acidic, it goes from that to tasting chalky and also weird, like fishy weird. And so this is obviously a problem. But for every negative charge that's in water, you have to have a positive charge. Think of that Nobel Prize 1903, Arrhenius, who says, well, yeah, if there's one bicarb, we have to have one positive charge as well. And by far the most prevalent positive charges that you're going to find in coffee brewing water are sodium, potassium, calcium, and magnesium. And the way we like to think about what's happening is you have a coffee particle with some things hanging out of it. Calcium comes by, which is positive. It sees these negative sides. It grabs onto them, and next thing you know, you've got benzoic acid floating around in the liquid, and it's no longer in the coffee. And so we initially posited it was like add calcium and magnesium, and you're going to increase extraction of things we like to taste. And that over the years, people have said, well, what if we just added the magnesium and the calcium afterwards, after we brewed it? We'll show that in just a second. But what I want you to imagine of what's happening is that the calcium is going to bind to things that are electron-rich, like oxygen. It's not going to bind things that don't have electron-rich motifs like alpha-pinene. This is important because theaflavin is one of the compounds that makes Ethiopian washed coffees taste like black tea. And so if you have calcium and magnesium around, it's going to interact with it. And this compound, alpha-pinene, is one of the compounds that makes chamomile tea taste like chamomile tea. And if you have calcium and magnesium around, it's going to not interact with it. It's going to exclude it. So already you can see that there's a problem. Water for coffee and water for tea are different. That's a problem for a cafe. That is your problem, not my problem. Okay. So do ions really help in extraction? The coffee literature sucks. And as you probably saw when you signed up, I was going to give you a talk about all the things we learned since doing my podcast, Coffee Literature Review. Instead, I will say I didn't want to do that because I would just stand up here and be really negative about all these crappy papers. So I had to go diving into the world of tea. So these are a couple of papers published on tea. In this case, this tap water is hard, and we're going to compare it to reverse osmosis and deionized water, which are much the same. Okay, mineral soft versus TW, which is tap water, which is hard. And we're going to see that for this tea, they managed to extract whatever the units of this are. 1.52 is bigger than 1.36. In other words, when we have metal ions around, we got more caffeine out of this tea. And in this study, tap water's hard again, different paper, and you can see soft water is bottled and deionized. They made the conclusion that the green tea was more green and the black tea was more brown when brewed with higher ionic content water. That is, I have no idea what makes it more green or brown. That's not the point. The point is, it changed what you extracted. And because of that, it may be true that if you add ions before or after, they may taste the same, but it doesn't undermine the point that it does change what you extract, okay? Having said that, adding ions afterwards is a great way to experience the impact of the flavors of the minerals you're adding. So there are products on the market that do this, and you should play with those. But you need to know what's in the water. So you can't just start blindly adding things. So we're all here. How many people are from a hard water location? So for all of you, I'm sorry, your coffee at home probably is terrible, right? But you also now fully appreciate the impact of what the heck I'm talking about, is you go into a cafe who's got a fancy water filtration system, and you have this excellent experience, and you're like, perfect, I'm gonna buy the Esmeralda, I'm gonna spend $80 a bag, and you bring it home, it tastes like a bona fide fish sauce, and you're like, I don't get it. You need to know what's in your water. So the way you're gonna have to measure it is a variety of techniques that we have to go through briefly. The original one was this little pen that looked something like my laser pointer. You'd put it in a cup and you'd measure the response to an applied electric field. Basically, the ions would respond to an alternating current polarized electrodes. The extent to which they responded gave you a signal, and it was typically reported in micro or millisiemens per centimeter. But at some point, we transitioned that into ppm. Maybe in question time we can go into why that is. But here's the problem with this device, is that if the water contains a little bit of hydronium, if the water's acidic, it conducts a heck of a lot more than if it just contains some salt. Same molar ratio. So if I have 1 mole of H+, it's gonna conduct 7 times more than if I have 1 mole of sodium. So you get the idea of this device, if you don't know what's in the water and you put your thing in and you read 100, is that 100 because it's all of this, or is it 100 because it's got a lot of that? We don't know. I was met with some feedback on this 10 years ago by a famous now TikToker, and this job takes you to weird places, you see. So, and I challenged him, I was like, if you believe in this device so much, how about I make the water, you get to use the device, one of them is gonna contain uranium dioxide. You get the point. That's not good. This device also struggles when you make concentrates, because at some point the water is so hard that the ions don't freely move around, they run into each other and stick. That's a bit of a problem. Fortunately, in coffee water, we're down in this zone down here, so it is still linear in that range, which means if you know what you're adding to the water, this device will tell you the expected conductivity. If you start making concentrates, the conductivity diverges from the expectation, so the device becomes less useful. The best thing you can do is titrate. So you take a known amount of water, your brewing water, you're gonna then add something that has a known molar ratio or concentration of the thing you're adding to that water, and at some point, once the reaction is complete, you're gonna see this go red, 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 blue. Or in this one, it's blue, 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 red, okay? So at that moment, you just count the number of drops you've added, and that corresponds to whatever you were trying to measure. In the lab, we have this thing called a burette, which is just has little incremental volumetric notes on it, and you're gonna add, so you take the initial volume, you drop some in, you measure the final volume, the difference is how much you've added, obvious. What we're actually doing here when we're looking for calcium is we're adding the molecule EDTA, which is the molecule you take if you have lead poisoning. And so it just binds up all the calcium, and at some point, there's no more calcium to be bound up, and so there's a color change, and that's what gives rise to the solution going from red to purple. What you're actually doing is we are traversing along these plots here. So let's say we're starting here with some unknown concentration. We start adding a mole ratio of whatever, we're adding some stuff to it. And at some point when we've got exactly 1-to-1, we have a very large amplified response. And so you don't ever see this plot, but this is what's happening, is like drop, 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 and then all of a sudden big change, right? Okay, so that's a titration. And if you want to do it to your brew water or your house water, I strongly recommend this Red Sea Reef Foundation Pro because it allows you to separate magnesium and calcium. This is actually made for keeping coral. So any of you that have a coral enclosure, I guess coral cares about magnesium as much as coffee people do. I don't know. Okay, so here, some of you are taking a photo. Take your photo. Nice. Okay, so here we are. We are up to speed. We are good. We got 20 minutes. We're cruising. It's now time to apply it to coffee. It's a lot of words. This is how, imagine being in Gen Chem with me for 10 weeks, 4 times a week. It's incredible. All right, so, and it's always like this, I promise. We have a problem. So I come here and a barista competitor, a Brewer's Cup competitor comes up to me and says, I want to talk to you about water quality. It's like, which quality? We just went through 1 million of them, okay? And the problem is that what we really mean when we say water quality is that high quality water is water we like to drink. But it doesn't mean it has qualities that make tasty coffee. And so most of the time, people who say they've got really high quality water, like people in Oregon, say it because they have soft water, because these red dots are places that we've been, and in these places they tend to have soft water, which makes pretty tasty drinking water. We'll see that it's maybe not perfect for brewing coffee, but the point is that we're no longer talking about this. And part of the reason I don't like it is because even within a small country like England, you can see that, or well, in this case, this is all of the UK. So you can see that as you go from Scotland where it's soft down to London where it's hard, that's only in the span of like hundreds of miles. We've had massive differences in water chemistry, let alone places like Massachusetts, where on the north side of the Charles River, you get fed by different water than on the south side in Boston. This is a complicated problem. So the only way you're going to know what's in your water is by doing that titration. You have to do it. There's no way around it. Or you could send it out to a lab, but I'm telling you, the titration's great. Also, I have a YouTube video on how to do it. It's really boring. It's great. We can spend more time together. Okay. So all water, regardless of its use, whether you're brewing coffee or whatever, should be filtered through carbon. The reason is the water picks up molecules on its journey from municipal water treatment facilities to your house. It's going to dissolve things in the pipes. And we're not talking about ions here. We're talking about organic compounds and whether or not the water's been chlorinated. You get the idea. So when you go through carbon, which is just actually the husks of coconut that have been roasted, because there's literally nothing else in the world that we can use those for, we make activated charcoal, and that is what absorbs the different compounds from drinking water. When you do that, that water now won't have color, and it won't have odor, and it won't have the taste of organics, but you did not affect the ionic content of the water, the things that can cause the problems of making coffee taste crappy. So if you want to do that, you're going to need to do ion exchange. And the way does anyone here have a sodium chloride water softener that they have to do? Yeah, yes, awesome. Terrible for coffee. Worst thing ever. Okay, so I'm going to explain to you how this works for everyone who has never seen one of these. Basically, the device feeds the whole house. Hard water comes in, rich in calcium and carbonate. And if you don't treat it, you turn on hot water, it's going to deposit white minerals at the taps, everywhere that water touches. Causes a big problem. So you could alleviate the lime scale buildup by targeting either removal of calcium or the removal of bicarbonate. It's really easy to remove bicarbonate. The way you do it is you have a resin. The resin basically has little tiny molecular level tendrils that poke out, and you're going to cover those tendrils in sodium. Okay, so periodically you're going to run out of sodium, so you're going to have to refill the sodium chloride back in the tank. But the tendrils are covered in sodium. But these tendrils would much rather be covered in calcium. So as the calcium-rich water flows in, blue dots are calcium, calcium sticks, and the black and white dots, which you can think of as sodium, then come into the water. So that's a substitution. Why this is bad for coffee is that we just took out calcium and we left all of the bicarbonate that was there already. So now we've lost the extracting power and we've kept the buffering power. So that's like the worst thing that can happen. So I'm very sorry for you, but it's okay. Like, it's fine. There's other solutions. The other option here is you can have the same tendrils, but coat them not only in sodium, but also in protons, hydrogen. When you do that, those hydrogens can react with bicarbonate. So now you're doing the substitution of calcium out, sodium in, and bicarbonate passes by the protons and will turn into carbonic acid. And as we know, carbonic acid will decompose and it'll turn into water and CO2. It bubbles. So some of us have seen one of these ion exchange resins. They have a little bleed valve at the top that actually releases CO2 as it evolves. Same technology as the one that feeds your house, different ions on the resin surface. Okay, ion exchange works nice. The other option is reverse osmosis, but before we go in reverse, let's do forward osmosis. So the idea here is that we have this U-shaped receptacle with a membrane in the middle that allows water to go one way but not the other, or actually allows it to go both ways, that's fine. And in this case, we have low concentration black dots and high concentration black dots on either side. Osmosis is the process of water doing work to seemingly oppose gravity so that both sides of that U-shaped thing become the same concentration in black dots. So you can see that's what I tried to draw for you here. This side and this side are now like close in concentration. Reverse osmosis is the opposite. So now we're going to do work to concentrate one side, so all the ions end up on one side, and on the other side, the water comes out as seemingly pure water. So that's what I try to draw for you here. It's like in comes the water, we remove sand and dirt. Then we remove organic molecules that smell bad. And then we go through the reverse osmosis semi-permeable membrane. It's semi-permeable because it allows water through, but not ions through. The water comes out the sides, and that's what goes as demineralized water. And then all the ions go out this waste stream right here, and you can do whatever you want with it. You could even blend some of it back into the water. And if you do that, then you don't end up with pure reverse osmosis water. It's like reverse osmosis plus a little bit of the incoming stream. And if your water is well suited to that, you can make reasonably tasty brewing water. Another thing that has showed up in the last 10 years is reverse osmosis followed by mineralization. Has anyone got one of these devices in the cafe? Yeah. One of the challenges with these mineralization cartridges is that overnight, basically water sits in the cartridge and gets more and more concentrated with the minerals, so the first flush in the morning is higher in concentration. But worse than that is that most salts, as you heat up the water, become more soluble. But calcium carbonate, as you heat it up, becomes less soluble, which means that a calcite remineralization cartridge works worse as the room heats up, which is as the day starts. So the device becomes worse and worse at making reasonable coffee. So we've experienced this. I'm sure some of you have tried it. Okay, so what are we trying to do? We want to protect the equipment. We don't want limescale, but we want tasty coffee. So we don't want to remove the calcium. We want to have a designer amount of bicarbonate, and we want to be able to extract things we like and not things that we don't. So the summary is we want calcium, but not too much because it crystallizes. We want bicarbonate, but not too much because then it wipes out the acid. We don't want chloride. I didn't show you why, but it kills the stainless steel, so that's going to be bad. And so overall, we just got to figure out a balance somehow that makes tasty coffee. All right, so then we have a problem. I give you this spiel, and then I say, now make me it, but then the roaster gets involved and goes, well, I'm going to turn this thing from green to brown, or black, whatever. And inevitably, they're following some profile, and then the next person comes along, and they follow a different profile, and now all the acid content's all over the place. It's extremely hard to know what water I need for which coffee, right? I don't want to buffer too much. So then you're like, well, what the heck is in coffee? A lot. Okay, good. Let's move on. So, and who cares? Because it turns out like one of the grand challenges in sensory science is relating a molecule to a flavor. Usually it's more complicated than one-to-one. So what we actually care about is something that looks like this, whereas the carbonate hardness increases, what panels do we see affected by increasing bicarbonate? The way I actually did this math was I went around the outside of the wheel and I looked at the molecules that give rise to the flavors of the World Coffee Research reference preparations. What that means is that we're making the assumption that when we see blueberry, which is, okay, blueberry is a bad example, it's not written. Let's pick clove. When we see clove there, the flavor of clove in real clove and the flavor of clove in coffee, I'm making the assumption those are the same molecule. They may not be. That doesn't matter. The exercise is merely showing you we lose panels of the wheel. Let's do it static. Here's my wheel for water for coffee. You can see there's some valuable additions and subtractions. Vine-ripened tomato, it has been added. What a moment. Vanilla and vanillin have been combined. You get the idea. Why I show you this is because we lose all the fruit, all the acid-driven flavors, and we lose a heck of a lot of the things we value. Some stuff survives. What about this weird one? Why do we still have floral? Because I would think that like when we have hard water, we don't usually taste those nuanced floral flavors. That's by construction of how we did this. For example, if you look at the molecules that give rise to the flavor of jasmine and jasmine tea, none of these molecules are affected by bicarbonate. Therefore, the way I constructed the wheel, they should not be wiped out by having bicarbonate around. Whether they are in real life is a different problem, but I use this as an illustration. So the summary here is that magnesium, calcium, I think extract flavor and also taste sweet. To me, calcium's sweet. Bicarbonate structures the flavor. We then have to extract coffee. So here's sort of like the summary and maybe a couple more slides on it. Filter coffee is a lot of water and not a lot of coffee. So if we add a lot of water, you're adding a lot of minerals. So typically you're going to want to imagine that filter coffee is going to not want nearly as much bicarbonate as you might want for a more concentrated preparation. And then also, there's going to be a limit to how much you want to extract because you're brewing for a while. And so there's a possibility that with calcium and magnesium around, you're going to start to get like pretty heavy compounds make their way into the cup if you use too much of calcium and magnesium. So this is our like little window here where we think that if you're in that window with filter coffee, you're gonna make pretty tasty coffee, independent of who roasted it. This is the window for espresso. And the reason is, as we'll show in a minute, the math is that espresso is 10 times more concentrated, but imagine it's the same molecules. You're gonna have to have more bicarbonate to deal with those 10 times more concentrated acid molecules. In reality, I've never had an espresso that's been prepared with water that's too hard. I've had an espresso that's too hard for the machine, but not too hard for my palate. And we'll see from mathematically why that's probably true. But here is the water for coffee, right? So this overlapping region is the region that if you had to pick a water that was gonna service your filter bar and your espresso bar, I would probably wanna hit somewhere in this blue zone, because in there you can do things like overdose or underdose the portafilter. You can play with grind setting. You can do the stuff you always do and not worry about the water. Outside of that zone, you're gonna have to work pretty hard. So let's say you have water over here and you're trying to brew filter with it. You're probably gonna wanna updose because you're gonna want a lot more acid making its way into the cup, right? So you get the idea. It's kind of like a push and pull. So to conclude, let's go briefly through why water for filter and water for espresso are different. Let us imagine that we're using 20 grams of coffee to prepare espresso, and the same coffee is brewed as filter. And we're able to achieve a 20% extraction yield, which is 4 grams of the coffee dry mass ends up solvated in the cup. So let us also then assume that of those 4 grams, there's the same amount of acid in that one as there is in this one, okay? From a mole perspective, right? The same number of acid molecules in filter cup as in espresso cup. But the espresso cup is 10 times smaller in volume. So the espresso here uses 40 milliliters of water, and the water, let's say, contains 50 milligrams per liter of bicarbonate. So if you look at this, that results in you having only 2 milligrams of bicarbonate floating around in the espresso cup. Conversely, if you use that same water to brew filter coffee, unsurprisingly, that cup now has 20 milligrams of bicarbonate floating around, dealing with the same number of acid molecules in solution. So obviously then you would say, well, it really depends on the coffee whether this is a big deal or not. I agree with you, but the executive point here is that the window for filter coffee's bicarbonate concentration is narrow, but it's narrow not because of the coffee, but because filter coffee is always between 1 and 1.5% TDS. It's a really narrow window of concentration. When you look at capsules, lungos, these sorts of things, that window gets wider. It's somewhere between 4 and 5.5 TDS. When we go to espresso, we can argue about what the definition of espresso is. I don't care about that. Let's say TDS 7 and above is what espresso is now. Well, that's a bigger window for what you can deal with in terms of bicarbonate, right? Because that's a handle you can turn and say, oh, I have high bicarbonate today. Let's go for a more concentrated cup to overcome that problem. So with that in mind, if you have hard water and you're struggling, just make smaller drinks. Use less water, less ions, less problem. So with that in mind, this is the last slide. If you ever have if you're sitting here thinking what to glean from it, bicarbonate is an issue, and if it is your issue, then make small drinks. The second thing is that you want to have softer water for filter coffee than you do for espresso. And if your bar in your cafe is set up such that you have a filter bar and an espresso bar with different water feedstocks, that's a great opportunity to explore 2 different treatment methods to access excellence on both parts of your business. And the last thing I'll say is that you may have noted that in our flavor wheel, some panels survived like chocolate and some of the spices. And that actually, I want to put the lens back on coffees that are typically scoring lower on these score sheets and the new descriptive analysis forms, because they do not have that implicit acidity, they don't have some of the things that are valued, but those things are also the ones that get wiped out in water. So I want to highlight Brazil, Sumatra, Hawaii, PNG, etc. These coffees actually tend to do well independent of the water you brew them in, because some of those flavors are just simply not affected by having bicarbonate around. So with that in mind, that's water for coffee. Thank you very much for tolerating it for 1 hour. We got 5 minutes. I'll take any questions.